Welcome to today's lesson. We are on Unit 6, Lines and Planes, and we are on Lesson 3, Intersections of Lines and Planes. Intersections of lines and planes. First, we're going to be taking a look at just intersections of lines. So intersections of lines, we're given two lines in 3 space. I'll just enlarge these so you can see them a little bit better. If we're given two lines in 3 space, we have 4 possibilities for intersections. The lines are either distinct and intersect at a point, so there is exactly one solution. Case 2, the lines are coincident, so they actually lay on top of each other and touch at every point. Therefore, there is an infinite number of solutions. The lines are parallel and distinct, so they'll never intersect, and therefore there will be no solutions. The lines are distinct but not parallel, and they do not intersect. And these are called skew lines, and again, there is no solutions. So looking at our first example, let's determine if these lines intersect, and if they do, find the coordinates of the points of intersection. Okay, so if the lines are coincident, then the coordinates of the point of the first line, or we'll say from the first line L1, will satisfy the equation in L2, so line 2. So we want to write the parametric equations for line 2, so let's go ahead and do that. So let's see, L2, so x is equal to 1 plus t. Y then is equal to minus 9 plus 5t. Z then is equal to 9 minus 2t. Okay, so let's take the point from L1, so the first line, so 5 and 2. Okay, so we're going to plug them into the parametric equation for line 2. And what that's going to give us, okay, so it's going to give us 3 equations. So we'll have 5 is equal to 1 plus t. Okay, then we're given 11 minus equals to negative 9 plus 5t. Z is equal to, we'll say that's 2. Let's change that. 2 is equal to 9 minus 2t. Okay, so let's isolate for t. So t then is equal to 4 in this case. And then what we have here is 20 is equal to 5t. So t then is equal to 4. Okay, so we have 2 out of the 3 so far. So negative 7 is equal to 2, negative 2t. So t is equal to roughly 3.5. Okay, so we've got 2 out of the 3, but not all 3. Since the t values are not identical, that means the point from line 1, okay, does not lie on line 2. The lines are then parallel and distinct. Since the values of t's are close to one another, we can conclude that they're probably relatively close to each other, but they are parallel and distinct. If the value of t was all the same, then we have one solution. Okay, so which means that the point actually does lie on line 2. So if we were to then take that value of t that we found, we can actually plug it back into the parametric equation of line 2 and find the point of intersection. But in this case, they're not all distinct, or they're not all the same, so that means that they are parallel and distinct. Let's take a look at example number 2. Example number 2 asks us if these lines are skew. Remember that skew lines means that the two lines are not parallel, however, they will never intersect. So in skewed lines, there is no solution. So the first thing that we should do in solving this question is eliminate the case in which the two lines are parallel. And the way we can do that is compare their direction vectors. So M1, okay, is equal to 1, 2, and 3. M2 is 2, -1, and -1. Okay, so they are different. If they were parallel, okay, so M1, now if I could have drawn this a little bit better, you would have seen that they were parallel. If they were parallel, that means that the two direction vectors, okay, would just be scalar multiples of each other. In looking at this, it doesn't look like they are, so we can conclude that M1 is not a scalar multiple of M2, okay, and they're also not equal, so it means they're not parallel. Okay, so now what we can do is then determine if we can come up with either a solution or a point of intersection. Okay, if they're skewed lines, then they will never intersect. So although they are not parallel, they could still have a distinct solution. So that's what we have to determine. So what we can do now, what I'm going to do is actually write the parametric equations of both of the lines. Okay, I find this the easiest way to do it. So x is equal to 5 plus s. Y then is equal to, for line 1, -4 plus 2s. Z is equal to -2 plus 3s. Okay, so line 2 then, x is equal to 2 plus 2t. Y is equal to -t. And z is then equal to 1 minus t. Okay, so I have the parametric equations for both lines. Okay, so we will now solve for s and t. And s and t should be able to satisfy one other equation in either lines, either line 1 or line 2. Okay, so what I'm going to do now is take my x's and equate them to each other and solve for, and I'm going to come up with an equation. So in this case here, what we have is 5 plus s is equal to 2 plus 2t. Okay, so that's equation number 1. Let's see now. Let's rearrange this a little bit nicer. So what we have is, this over here, so s minus 2t is equal to -3. So that's 1. Equation number 2, over here, again, I probably haven't left myself that much room. Why don't we go over here? So -4 plus 2s is equal to -t. 2s plus t, I'll move this t over here, is equal to 4. Okay, so we'll call that 2. And then over here at number 3, we'll say is -1, 2, and then 3. So -2 plus 3s is equal to 1 minus t. 3s plus t is then equal to 3. So we have our 3 equations. Okay, so let's sub one into the other. Okay, so we'll isolate one of the variables. So in this case, I would isolate this one. S is then equal to 2t minus 3. Okay, there we are. We're going to take that and plug it into, let's see, let's plug it into this one. Plug it into number 2. So 2, this is 1. So this is 1 into 2. Okay, so 2 times 2t minus 3 plus t is equal to 4. 4t minus 6 plus t is equal to 4. So 5t is equal to 10. T then is equal to 2. Okay, so t is equal to 2. I can now take this and plug that into, let's say, number 3 and find s. Okay, so 3s plus 2 is equal to 3. and now 3s is equal to 1, s is equal to 1/3. Okay, so we're just transferring everything over to this new sheet of paper. So t we found was 2, s we said was 1/3. Okay, so let's choose 1. Let's take equation number 1. Okay, we said that equation number 1 was, I'll rewrite it, is equal to 2t minus 3. Okay, so let's plug all our values in of t and s. So s we said was 1/3. 2, we'll replace t with 2 minus 3. Okay, so this is left side equals right side. Oops. Left side, right side. Okay, so we're testing to see if the two are equal to each other. And in this case, it's 4 minus 3, which is equal to 1. So that means that the left side is not equal the right side. So there's no solution. Okay, so thus the lines, therefore, the lines do not intersect. Now, if we came up with something that satisfied one of these equations, okay, with values of s and t that we had solved for, then we would actually have a solution. Okay, so that would mean that we would then be able to find a distinct point of intersection. Okay, in this case, the lines do not intersect and are not parallel. Okay. Let's move on to intersections of lines and planes. So in lines and planes, we have 3 cases instead of 4. Okay, so the first case is if the line and the plane intersected at exactly 1 point. So there is one solution. The line lies on the plane so that every point on the line intersects with the plane. Therefore, there's infinite number of solutions. And then, of course, if the line is parallel to the plane, the line and the plane do not intersect, so there will not be any solution. Okay, and in this case, we don't have any skewed solutions because we're dealing with the line and the plane. Okay, looking at our first example, in each case, we're going to determine if the line and the plane intersect, and if so, we're going to determine the solution. So in part A, we're given these two lines, or this line and this plane. Okay, so let's see how we can answer this question. Okay, so what we do, the method in working out this problem is, let me write A. Markers are running out. Okay, so we'll take the parametric equation of the line and plug it into the scalar equation of the plane. And so then we should be able to then solve for the parameter. Okay, so I'm going to go ahead and do that. So 9, okay, 9 comes from the scalar equation of the plane. So plugging in for x, I would take the x coordinate of the line, 2t, okay, plus 13, negative 5 minus 5t, minus 2 plus 3t. Okay, working that out, so 45 plus 18t minus 65 minus 65t minus 4 minus 6t is equal to 29. Okay, so now we can just collect like terms. And what we'll get is negative 53t is equal to 53. So then t, we can say, is negative 1. Okay, so we have a value for t. Okay, what that means then is that we have a solution. So we can actually plug that into the parametric equation and come up with a point. So taking the parametric equation of the line, x then is equal to 5 plus 2, negative 1, 5 minus 5 then is equal to negative 5 minus 5t, which we said is negative 1, 0. Z then is equal to 2 plus 3 times negative 1, so negative 1. So our point of intersection, therefore intersection is 3, 0, and negative 1. So looking at B, okay, we're going to do the exact same thing. Okay, let's go ahead and do that here. Okay, so we'll go 4 plus 6t, so this is B, plus 3, negative 7 plus 2t, minus 4, 1 plus 3t is equal to 10. Okay, so that is 4 plus 6t minus 21 plus 6t minus 4 minus 12t is equal to 10. So the t's will actually cancel out, and we're left with 31. Okay, so this statement here is impossible. Okay, so which means that all the t's cancel out, so there is no t that will satisfy this equation. So there is no solution, which then means that the line is parallel to the plane and it's distinct. So it'll never intersect. So therefore, they are parallel and distinct. Okay? So that means the line is parallel to the plane and the line does not lie on the plane. Okay? So let's take a look at C. So I'm just going to click over again just to show you what it looked like. Okay, there it is there. Okay, so what we can do is, let's just do the same thing again. I know it gets repetitive, but you'll be really good at them by the end of this. Okay, so C part. So we'll do the same. Negative 2 plus 3t minus 4 plus t plus 11. 1 minus t is equal to negative 1. Okay, so minus 8 plus 12t minus 4 minus t plus 11 minus 11t is equal to negative 1. So what we get is 0t, again, okay, is equal to 0. So 0 t's equal to 0. That means that the equation is true for all values of t. So any point on the line is a solution. Therefore, the line lies on the plane. Okay, so therefore, the line and plane are coincident. Okay, because there's infinite number of solutions. Okay, so looking at our last example for today, without solving, we want to determine if the line intersects with the plane. Okay, so we're given a line and a plane. So how are we going to do this? Let's think about this for a second. What can we do in order to answer this question? What exactly are we given here? So we're given a line, we're given a point of the line, okay? What else are we given? We're given the direction vector of the line, and what can we get from the plane? What information can we just get from the scalar equation of plane? Well, what about the coefficients in front of these variables, x, y, and z? What information does that give us? Well, that gives us the coordinates for the normal. Okay, so what we have is a normal to the plane. We have a direction vector for the line and a point. Is there anything that we can do here? Okay, so I'm going to go ahead and write them out. So maybe that'll stir some thought. Okay, so my direction vector is 3, 2, and 1. Okay, and so my normal for the plane, taking again the coefficients, is 3, negative 1, and 1. Okay, so what can we do here? Well, let's first eliminate the case in which they are parallel. And how can we do that? Well, let's see. If these two, okay, remember that here we have a line, and here we have a plane. Okay, so this is the normal, and this is my direction vector. That means that if they're parallel, that my direction vector, my normal, should be perpendicular. Okay, so remember this property, if you will. or perpendicular. Okay, so let's do that. So m dot n then is equal to, so 3 times 3 is 9, plus -2 plus 1. So it is a number, so that means they are not perpendicular. Okay, so they're not perpendicular to each other. That means the lines, therefore lines, are not parallel. Okay, so that takes care of that. Okay, so think back. We only had 3 scenarios. So we either could have said that, well, they're parallel, okay, or they're coincident. And in this case, by doing the dot product, we've eliminated 2 cases. So we are only really left with 1. So we can conclude that the line and the plane do intersect at one single point. Okay, and that's all the question really asks of us. Okay, so we've answered the question. Okay, so this concludes our lesson for today. I hope you have a great day. Remember to do some practice, and we'll see you next time.